Hey guys, this is Tom Cherryholmes with another Retro Computing Archaeology series video. This is going to be kind of impromptu because this just got working and I'll make a more in-depth video once I get more of the pieces running here. But the long story is we've been able to resurrect the CAMAC assembler that's been running, that hasn't run for more than 40 years because we didn't have a full environment to actually do it in. So what is CAMAC? CAMAC was the cross assembler that Atari used to do their assembly tasks. So basically, the home computer division at Atari had an MV8000, which they used for all their software engineers. An MV8000 is roughly equivalent to, say, a DEC VAX 11780. In fact, a little bit faster. It runs at about 1.5 MIPS as compared to the 1 MIPS of the 11780. So it's a pretty beefy little machine. Comes with at least 256K of memory. It can have up to like 16 megabytes of memory on it with all the freaking stops pulled out. So it's, it could be a pretty beefy little machine. So it's roughly equivalent, 32-bit machine, roughly equivalent to a VAX. And what they literally did was they took the ATARI macro assembler and then they ported that over to run as is inside this environment here. And thanks to wonderful work over at Nobazar Forever and all of those guys, we've been able to put together an emulator to basically take and run this damn thing. So this emulator is based in SimH here, and we're going to take and start it up. And it's going to wait for a telnet connection, which we'll take and do. Okay, no problem. We use this so I can use an actual dasher terminal to do the work here. We're now connected to the WildHair MV emulator. We're emulating an MV8000 running the AOS VS operating system. This is an operating system that provides both interactive and batch processing facilities, multitasking, the whole works. I'm sharing. So we're going to be the only people on this system here. And in case you're noticing right here, this MIPS value is extremely large. Recall that I said that this machine ran at about 1.5 MIPS, so we're running roughly about 100 times faster. This is going to run very fast. We're going to go ahead and boot into the system here. This would normally take about 2 or 3 minutes to take and do a full bring up here. This is pretty much going to be instantaneous once the disks actually come up to speed here. So, yep, okay, there we go. And now we're in the 16-bit Eclipse CLI environment here. We're going to take and execute CLI 32 so we can wind up in the 32-bit environment because that's what CAMAC needs to function. At which point, I will take and abuse the system a little bit here, giving myself super user privileges so I can bounce around this thing like I would need to. And for this particular thing, I'm actually going to take and change the directory to CAMAC. I'm going to change the directory to 01, and we'll take a look inside of the this directory here. Just do a file status on all this here. So what Atari actually did was Atari took the AMAC source code. It's actually in directory 00, and they algorithmically converted it all. These are the individual source files into instructions that the MV8000 could actually execute. They ported it as is. And they also even ported over the eccentricities of the Atari operating system here, the CIO, the SIO, etc., to the point where we have to use Atari device specifications to specify file paths. It's a bit bizarre, but it works. It's a bit strange. And to basically show that this actually works as expected, we can actually take, and I will change directory again into digrom here. And if we take a look, this is where we are currently inside the system. So we've got CAMAC 01 and digrom here. And if I do a file status on this, this is the source code for all of DigDug and all the little build scripts, all the backup files, all the editor control files, and everything, so that source code can be edited here too. Once I get the editors and everything working again, I'll take and show how they actually did source code editing and whatnot on this system too, because you could do that on this machine. So to take and build this, all we have to do is invoke CAMAC. And here's the funny thing, if you've seen how AMAC works, watch this. It literally looks exactly the same, except instead of saying ATARI Macro Assembler, it's ATARI CAMAC Assembler 1.08, enter source file name and options. Now, when we enter in the source file, this is the funny part. We actually have to enter in a device specification here, a fake one. It ignores it and skips over it, but we have to provide it nonetheless, right? So I will say digdug.asm, and I want the output to be digdug.obj. I also want the listing to be digdug.prt, a list file, or list, make it a list file. And I want full cross-referencing here. So once we do that, it takes and does the full assembly here. And because this machine's running much faster than the actual machine, it just took and spit that out very quickly. But you can see that if you watched my native assembly here, you'll notice a couple of things. One, you'll notice that we have a bit more RAM free to take and do our assembly here. We have a lot more actually to take even after assembling all of that. So we're able to do all of this with the listings and the cross-referencing and spit out everything that we needed to spit out here. So now that we're done, we can exit. We're back at our prompt. And at this point, if we take and do our little look here, we can see that we have our digdug object file output. And if we do a look, and you paid attention to the last video I did, you'll see that it's the same file size here, 16.629. And this is actually a binary loadable copy of digdug here. On the actual HCD machine, they had their own loader that you could take and load this into to spit out a memory image for a cartridge. We don't have that here, so I had to take and create my own on my main PC here. So what we're actually going to do is we're going to take this file out of the system via tape. And to do that, I'm going to take and break out of the simulation for a moment and attach a tape here to the main tape drive. And we're going to call it digdug.tap, create new file. And we're going to continue the simulation here. And what I'm going to do is I'm going to tar, I'm going to say create file, and it's going to be PC0, file number 0. Okay, great. And it's going to consist of digdug.obj, and it's going to consist of digdug.lst. Those two files are now bounced across. And I'm now going to take and we're going to take and just kind of go to the side here and pull these files out. So for that, I will take and open up a new window here. And if we take a look, we'll see our digdug TAP file here with both of the bits and pieces that we need here. But I need to take and do a little bit of processing. Hold on a moment. Sorry, I had a brain fart and forgot what the name of the utility was here. So I need to use raw tape, and I need to peel this away. Raw tape E, and I need to take and peel away the tar file here from that container. So digdug.tap, this is going to come out as 0001 dat. That's fine. It's just, take a look and see what that is. It's just a standard POSIX tar archive. No problem. We can take and move that. All that digdug tar. Extract it. And we have our digdug obj and list file, right? So if we take a look at our digdug list file, we'll find our CAMAC assembler, page 1, page 2, page 3, and there is our listing in all of its glory, matching the one that was already saved on there exactly. Groovy, right? Remember though that in our last video, we actually built a utility to take and do a loader. So we're going to go ahead and add DigDug object into our loader and out as a memory image. And we'll see that we now have a 64K memory image, which consists of our DigDug here. No problem. Now to deal with it, all I really have to do is use DD here. We're going to take and dig OF, and we're going to call it digdug.rom. And we're going to skip the first 32K. And I'm going to say count 1634 with a byte size of 1. This gives us a 16K image, which the reason I did that, for those who didn't catch the last video, when I wrote the loader, it's outputting to a virtual 64K memory space, which goes all the way down until we hit the cartridge area. And then the cartridge area comes all the way down. Cartridge header at the end of the cartridge area here. So everything's good. We just have to trim off the fat, which we just did with the DD here. And now we have a ROM. And if I take and now run that ROM, okay, sorry, I had to get my ATAR emulator up. If we take and run that resulting ROM now, I'm going to take and go all the way back into my vintage folder here. Go into my MV8000 folder here. There's our DigDug ROM, 16K ROM, and there's DigDug ready to go. So we've taken, with this little bit right here, we took and built a copy of DigDug as it was built using the ATARI macro assembler here, generated a listing file, took and bounced it out, and sent it over to our other machine here where we could actually finish the loading process and create a ROM from that loaded file. So with that, I'll end the video here, guys. What do you think? For the first time in 40 some odd years, CAMAC lives again, and we can take and look at it and study it so we can actually see how it actually worked. So here we go.